All right. So you can see that I have several stuff over here. Now, the first line tells latex that I want an A4 paper. It's really self-explanatory. Now I want to load some packages that allow me to show the fonts the way I want. After that, I'm gonna set the margins so this is all nice, neat, and centered. Then I load up necessary packages. This allows me to write equations. This allows me to write in blue, for example. This lets me use this vignettes. And this is just a better way of life package that allows me to insert and enters or breakup of lines just using enter. So how you style a general latex document? You write the title, author, and date. These are all already pre-existent functions. And you click and you write begin document. So when you write begin document, latex assumes that everything that comes up before is just set up. Make title allows you to insert whatever you wrote as title. And we're going to start out with a section. So our section, which appears bigger than the rest of the titles, because this is a subsection. Our first subsection is fair game. So we're going to review a little bit of probability. Okay? Let me do this. I'm gonna. And as you can see, if I save my document, it's going to update my view over here. Okay, so we have the following exercise. Can you guys read correctly what it says over here? Hello? Okay, great. Right. Before I continue, I'm gonna take attendance. Álvaro Adriansen. Sebastián Aybar. Mauricio Barrios. Yelena Borja. Estuardo Chalán. Sebastián Collantes. Jean-Pierre Espinosa. Xiaomi García. Roy Portilla. Fernando Ruiz. Sebastián Salinas. Giuseppe Valeriani. Andrés Vircaguamán. And Marcelo Villar. Okay, let's go on. I didn't catch if you guys could read this correctly. Can you? Okay, great. So let's read out the question. So you have a player that tosses a die, a normal die, a 1 to 6 die with equal weightings on which number can show up in its face-up value. So you have the same probability that you get a 1, you get a 2, you get a 3, you get a 4, you get a 5, you get a 6. Now the payoff is $1 for each dot on the upturned face, which is the same as saying, I'm going to pay you $1 times whatever number pops up, right? Assuming it's a fair die, which is a normal die, at what level should you set the ticket price for this game? So basically, is what is the minimum amount of money that you should charge in order for you not to lose money on average? Now, anybody has a clue. So you remember maybe on either microeconomics for finance or microeconomics 2, depending on which one you took, you have this concept of fair games. Now, the concept of fair games tells you that the expected winnings has to be netted out from both sides, has to be 0. So everything has to be a zero-sum game. Do you guys remember that? So basically, let me check if I can use the Blackboard tools in order to write over this. I don't think I. No. Looks like I can't. Okay. So I can do this. I have a regular die. My die is basically a uniform distribution. Let me correct myself. My die is basically, say my die is X. My die is basically a uniform distribution that goes from 1 to 6. Now, it's not really uniform, it's uniform discrete because I cannot get the in-between values, right? Now, this has a specific name, but we're not going to delve into that. What this means is that I have the same probability of X being 1 than X being 2, and so on until I can generalize like this, right? So if I want a fair game, that means I should charge whatever people are gonna win on average, right? So on average, we basically calculate an expected value, right? So what is the expected value of one roll of a die if every single one has the same probability? Correct. It's the mean. It's 3.5. Wait. Yeah, 3.5 is correct. Yeah. So let's take this opportunity to write it out over here. So the correct value you should charge is the average or the expected value of the winnings. Thus, the expected value of a roll, since it's a fair die, with 6 sides, will be 3.5. And if I save this, it'll show up on my right. Now we can go a little bit fancy. Let's say I want this to look equation-like. And I can do this. And check this out over here. If I save this, how it's gonna look. See? It's more formal, basically. Now I'm not going to leave. I'm not going to insert this thing. I'll leave it like this. So on the next page, we start with the next item. There we go. It's frozen. Oh, my bad. Apparently, I have to switch out from the next one every single time. I'm guessing you can see now or not. All right. So what I did is basically just write out this paragraph. And before, I just had this like this without the dollar signs. So what the dollar signs do on latex, it's still in latex to interpret whatever I write in between the dollar signs as an equation. And thus it's going to use its own font and its own logic to understand whatever's inside of it. So without the dollar signs, it looks like this. Hold on. There you go. Looks like this. With the dollar signs, it looks much better. I'm gonna put a dot over here. Now let's go into the next question. And I'm going to insert a new page as well over here. So the second question is that in the first exercise, we just roll the dice 1. Now, if I wanted to roll the die 3 times, and each time I roll, you can either take the number showing as dollars or roll again. What does that mean? Say on my first roll, I rolled a 6. Obviously, I want to take my winnings as 6. I don't want to roll any longer. If I roll 2, then maybe I'm feeling like on the next 2 rolls, I could roll something higher than a 2. Okay? So basically, and I'm going to write it over here. The logic of this will be if I roll once, then the expected value of my one roll, so rolling once, and this, what I'm doing right now, means sub-index. I believe it's like this. Pretty sure it's like this. We'll see. Yeah, I get a preview over here. So this underscore means that I want a sub-index. So the expected value of rolling once, we already decided at 3.5. Now if I roll twice, then think about it. I only want to roll again if I'm risk neutral, so I don't have any adversity nor risk lover, no risk averse. If I'm risk neutral, I want to roll whenever I'm feeling like my chances could be better. So if I roll something less than the average, I want to roll again, right? So if I roll twice, I just want to roll again. If my first roll was 3.5 or lower. Correct. Now, where does that leave us? That leaves us as what's your chances of rolling a 3.5 on the first roll? Oh, my bad. What's your chances? You cannot roll a 3.5 in a six die. What's your yeah, that's correct. What's your chance? What's your the probability that you roll 3.5 or lower? That was my original question. Yes, Fernando. It's 0.5 or 50%. So half of my distribution, by definition, because it's an uniform distribution, should be captured by the mean. So 0.5 is the probability that I roll out a 3.5. So 3 um 3.5 I'm just gonna take if I have half the chance. On half the chances I'm gonna just roll once. Now if I roll again, then my subset should no longer be 1, 2, and 3, right? So if I roll again, so my set over here was 1, 2, 3, 4, 5, 6. However, when I roll again, what am I striving for? I'm striving for something that's greater than 3.5. So 4, 5, 6. So of this one, my subset, yes. So if I roll, when I roll once, my expected value, so my expected winnings are 3.5. So, and 3.5, since it's the mean, and we're using a regular fair die follows a uniform distribution, the mean captures 50% of the distribution. By capturing 50% of the distribution, we have to multiply it by the probability, which is 0.5. So on 0.5 of the cases, I'm just gonna take my first roll. On the other 0.5 of the cases, I'm gonna strive for something greater. That something greater is between 4 and 6. So now my distribution narrows, right? I'm no longer using the whole distribution. So then the expected value of this new distribution is how much, guys? 5, correct. 5. And this yields you 4.25. So if I save my latex document, it's gonna show over here, and I have an error. So this is a good practice. Where's my error? Do 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 do. Do, 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 do. I believe there's no error. Let's save again. Yeah, it was no. There is an error. Oh, I get it. It's this thing. Should be fine now. What did I do? Let's see. Okay. There is something that I opened that I didn't close. So yeah, this is good practice that whenever you're coding, doesn't matter which language, you have to do error solving. I missed the item. Did I? No. The item, the backslash item, tells you that you can insert another vignette. This is assuming that if in the first trial you got a 6, you also try again. Sure, no. So if in the first trial you got something greater than 3.5, you're not gonna try it out again. And the chances of you having something over 3.5 is 0.5. Okay, so let's read this log. Line 29. No, this is a warning. This is not an error. Here's my error. Yeah, I'm missing. I believe it has to do with this. Yeah, sorry to be error solving. Damn it. Okay, I'm gonna do something simpler. Let's see where it errors out. Did it change something else? No. Okay, so, and no. Yeah, I'm gonna take the error solving for later. For now, I'm just going to leave it on black, and it should work, in theory. No, so it wasn't that. Okay, so I think it's this. Okay, I have no clue. This has to go in between equations, or else the the subscript that will not work. It's not this that's erroring out. Yeah, there's something that I don't know. So I'm just gonna type it out. But yeah, you get the general idea. So I'm just going to continue. So if I roll twice, then my expected value, so the fair value of a game of rolling twice should be 425. Now, if I roll thrice, then I just want to roll. If I get something on my third roll, I want something greater than 425, right? I just want to roll again if my first two rolls were 425 or lower. So my next set is 5 or 6, right? So again, what is the probability that I roll something that's below 425? So think of it in parts. What is the probability of getting any of the numbers in a die? Yeah, 1 over 6. So if I haven't rolled a 5 or a 6, then the rest of the probability, how much does it sum up? For 6, which is 1/3. 2/3. So 2/3 multiplied by 425, and then just the rest, right? 1/3 multiplied by my subset now is only 5 and 6. So my expected value should be 5.5, correct? So how much I should charge for a 3-roll game? I should charge, I don't know, I haven't calculated this one. How much is it, guys? So 2/3 multiply 425 plus 1/3 multiply 5.5. This is 466666666, etc. 466. Now imagine that instead of being just twice or thrice, if it's infinite rolls, how much should I charge for infinite rolls? Six. Why? Why? Why is it six? Because yes. So remember, this is a fair game. So in expected value, if you can roll infinitely, you will one day get a six for sure. So you will always win $6. That way you have to charge $6 for each for it to be a fair game, right? So it's correct. It's six. Okay. Let me try 1 second. No, okay. I'm gonna type it out just over on the left window, and then I'll pass you guys the solution whenever I figure out the error, because it should be somewhere. Okay. And in order to make your life easier, yes, that was what I was gonna do. I'm gonna erase all of this, save it on a notepad, and it should compile. Yes, it's compiling now. Okay, so miscellaneous. So let's get a little bit into distributions. We saw a little bit of uniform distributions right now, but let's get serious, right? So I'm gonna insert a new page. So we have a normal distribution that distributes with a known mean and variance, and we know that lambda is a value that's greater than 0. We have to calculate the expected value of a normal distribution squared. So if you remember that it's a chi-square distribution, and an exponential distribution, which takes into account normal values, that is multiplied by the lambda distribution, by a scalar that's lambda and is greater than 0. So text color blue. Okay, it's blue, right? Yeah. So what we have to find right now is the expected value. Let's go by steps, right? Expected value of x squared. And I'm gonna put an enter over here. Okay, so x squared, if you remember, the variance formula. The variance formula is something like this. A bar, or the fancy V, whatever you want to write, of x is equal to this minus something very similar to this. However, the exponent outside, right? Are you guys there with me? So they told us that we know the values from the distribution, that the mean is mu and the variance is sigma squared. So instead of variance, I will write out sigma squared, and instead of the mean, I will just write out mu. So I just have to rearrange my terms, and I already know what I'm looking for. So that was pretty simple, right? I believe you guys have no questions about. So let's go with the next one. Now with the next one, and I'm gonna do a whole other chunk just to make sure we're separating stuff. With the next one, color. Now the next one is a little bit less direct. We have to use our usual, not usual, but we have to use integrals. Okay? Now, what is the normal distribution as in a function? So the marginal function of a normal distribution, so I'm going to leave this right here. Normal distribution is like this. 1 over 1 over square of 2 pi sigma squared. All of this multiplied by let's just write out all of this multiplied by the exponential number to the power of minus and your distribution normalized. So x minus mu, however, it has a catch. This one is squared. All of this divided by 2 sigma squared. Now, this won't look fancy because I'm not using fractions. I'm just using divisors, okay? This will be useful for this question and whatever we're going to do next, okay? Now, is there anyone that didn't remember this or has any question about the normal distribution before we continue? I remember now, yeah. Yeah, so you don't usually have to remember stuff like this, don't worry. Okay, so we're gonna call this distribution. So before we go and solve the the expected value of whatever there's inside of here, so it's e to the power of lambda x. Let's remember a little bit how we solve expected values with integrals. So if I have e of x and its integral form, let's say of y, its integral form is, I believe it's sine t, yes. So I have it over the dominion. So each function has a dominion, right? So it has the lowest value that it can have and the greatest value that it can have. In the case of the normal distribution, it's minus infinite and plus infinite. However, let's go to our example in the die. In our die, the dominion went from 1 to 6. So let's do just a regular example. Say a is the lower bound and b is the upper bound. So the integral from a to b of y, so whatever is inside the expected value goes over here, multiplied by the marginal distribution of this distribution, evaluated on this variable, like this. Okay? Now, just another something to remember, if instead of expected value, you do variance, variance is like this. Variance is the variance of y, still integral, it's still from the whole dominion. However, instead of just y, we do the dy. Yeah, you do have to put the dy. Yeah. So instead of just the y over here, you have to centralize it. So y minus the mean, this to the power of 2, so squared, and the same. That's the difference when evaluating expected value and variance. Okay? So we're going to use this in order to answer the question of what's this? We could have also used it to answer this one. However, there's a much simpler way that we just saw, right? So I'm going to use double space for this. The expected value, let's forget the lambda for now. Okay, let's say the lambda is 1. Okay, just to make stuff simpler and calculations faster because we lost a lot of time for the technical issues. Let's say the lambda is 1. Then we just have to calculate the expected value of x, right? So expected value of x. Now since we know how to calculate an expected value, just copy this and replace the lower bound for normal distribution minus infinite, and the upper bound is infinity. Now, we said that wherever it goes inside of here is repeated over here, right? So this should be this should be e exp of x and the function of x evaluated in x, right? Which is the normal distribution function. This is a marginal distribution of the normal distribution. Okay. Nothing fancy yet. This is d of x. Nothing fancy yet. The trick. So something great with a normal distribution is that you can standardize it. And standardizing it allows you to do so much easier stuff. So any normal distribution can be written as the C distribution, so as a standard normal distribution, and you just have to transform it back, right? So any normal distribution that's just mu comma sigma squared is the same as saying a C distribution, which is a standard normal distribution, times that sigma plus that mu. Does anyone not understand why? I believe over here you have to write out the standard deviation and not the variance. No, it's the variance. Yeah, my bad. So yeah, anyone does not understand why? Yes. So what I mean by C is a standard normal distribution. So a standard normal is basically you take yeah, I'm gonna arrive at the answer with the question actually. So what is the operation that you always do when standardizing a variable? You take away the mean and you divide it by the standard deviation. So in order to get back the normal distribution from a standard deviation, you multiply it by the standard deviation and you sum the mean, right? So we're gonna replace our x with a standard normal distribution instead of a normal distribution. And that's gonna make stuff much, much easier for us. So we're gonna take our equation, we're gonna rewrite it. So instead of e2x, it'll be e2 mu plus sigma times z. And since now my only function is actually z, I can do this. So now we're not working with the normal distribution, we're working with the standard normal one. And the standard normal one is a little bit easier. The standard normal one goes like this. So standard normal, on parentheses, I'm going to put z, goes like this. So it's 1 over still square root of 2 pi. So to make it much easier, I'm going to copy this one. And we're going to replace values. Now, on a standard normal distribution, your mean, so your mu, is 0, right? So we don't have to take away anything here. And everything that was x is now just z. Sigma is 1. Again, over here, sigma is 1. Right? And this was from the sigma. So a standard normal distribution looks like this. Much simpler to use. Let's go back to this. Continue solving. So instead of f of x, f of c, I mean, we can just write out the standard normal distribution, which is this. I don't need these dollar signs over here. Like this. And now we just have to solve stuff. I'm gonna rearrange some terms. So this is all the same. So sigma z, this doesn't change. What I can do, for example, right now, is everything that doesn't have to do with z, I can take it out of the integral because it's a constant, right? So, for example, that part of 1 over, I'm just going to copy. So this thing, I'm missing this one. So this part can go outside because it's a constant. What else can go outside? E to the power of mu is a constant as well. So whenever you have e to the power of something plus something, you can separate it into e to the power of mu times e to the power of sigma z. So sigma z stays inside, and e to the power of mu we can move outside. How do I do what? Move a constant from outside of integral? That's a property of an integral. Basically, it's just rescaling something. Oh, select all the elements. This is not R. This is Visual Code Studio. That I also use sometimes to code in R. Yeah, that I also use sometimes to code in R. This is a great what's called is an IDE, which is basically a software that allows you to write and select, and it also gives you suggestions and how to fix stuff on on different programming languages, including latex. So, yeah, we moved out the e to the mu and everything else that's constant. So now inside the integral, we only have whatever has z inside of it. Now it's just pure math from now on, to be honest. So we're going to complete the square. I don't know if you guys remember that, but you can see that here we have a square, right? So we are going to complete the square. And this looks like this. And it's not too friendly. I'm gonna put a note over here. So note minus a half of c to the power, so c squared minus 2 sigma z. This is basically what we need to complete the square, right? Solving this out turns into minus, put some brackets over here, 1/2, or one half of c squared minus 2 sigma z plus sigma squared, sigma squared, all of this minus 1/2 sigma squared. Now we're going to use this square completing in order to change our previous answer. It'll transform like this. So I have everything that's a constant. I don't mind that. And it will turn out into, wait, this one. Yeah, it's this one that I gotta change. So inside this, we just put out whatever was inside that we solved over here. So this last one over here, all of this. It looks like I want, I think it does. Okay. Let's put it over on the right so you guys can see. Okay, and then look, now I have another term that doesn't depend on z. So I can take out that term. And my equation will look like this. And over here, instead of just mu, it's going to be mu plus sigma squared over 2. Okay, now we have not finished yet. We can still simplify stuff. Now, this whole chunk of things, remember, what we did was completing squares. And we completed squares for a reason, so we can reduce the square later. So now we can reduce that square. So over here, what we have now is minus z minus sigma, all of that squared. And I forgot over here the 1/2. So it's starting to look a little bit smaller, right? Just so you guys don't panic out any longer. Yeah, that's fine. Now, I want you guys to realize something. This is my bad. I've been copying this part that I shouldn't for like 3 lines already. So this one, this one. Where is this? This one. This one, I already merged this one into the squares. And the last one, I think. Yes. Okay. Now we're good. Now it makes sense. All right. So if I'm gonna zoom over here, can somebody tell me what is the result of this? Anyone? Now I'm gonna give you a hint. Look at the standard normal distribution. No? No takers? Hello? Okay. Oh well. Okay, somebody wrote. I forget. You don't have to know how to integrate. It's it's just plainly looking at the standard normal distribution and popping out a value just like that. So I'm gonna tell you the answer. So the answer is 1. And why is the answer 1? Because if you look, quick math. So if you look at the standard normal distribution, forget the constant, because the constant in any integral you can just take out. So the important part is that it's minus a standard normal distribution to the squared divided by 2. And over here, we have something very similar. We have the standard normal distribution taken out with a mean, so it's basically a standard normal distribution that's been shifted to the left. But it's still the same distribution, right? Whenever you're shifting something left or right, you still have the same shape of a curve. And since I'm taking it on the whole dominion, the sum of probabilities is always 1. Yes. So, since this is 1, so since all of this is 1, the answer is whatever's left, right? So this. I'm going to put another one over here. Yes. And I'm gonna use the board for once. So you have a distribution. If this is a normal distribution, then this is mu, right? If you have a standard normal distribution, this should be 0. Okay? And then all the properties of a normal distribution, right? D is equals 1, etc. Okay. Okay. Yeah. So the area beneath this curve, so the integral of all of this from minus infinity to infinity of any probabilistic distribution, it doesn't matter if it's a normal distribution, a standard normal distribution, a uniform distribution, the area beneath the curve, so the integral on all the dominion, will always be 1. Okay? So far so good? My symbols. So this in the middle is mu, so the mean. This on the left is an integral. This on the right is a sigma. And this is a 1. So if we go back into if we go back over here, then we know that this looks eerily similar to a standard normal distribution, because we saw that a standard normal distribution is like this. And whenever you're doing integrals, constants don't matter, right? So this thing and this thing are almost the same. Now, I'll write it even better in order for you to see that it's actually the same. So this thing, I'm gonna put before instead of the -1. So it's basically the same idea, right? The only difference that you have is that instead of C is C minus sigma. And any distribution, yes. No, you don't discard everything. You take everything. It's the other way around. You take everything. And since it's everything and it's a probabilistic distribution, it sums up to 1. So all of these things, 1. Then 1 multiplied by anything is that anything. Okay? We good? Does anybody not understand this? Okay, great. So I'm assuming you guys are really comfortable with turning any exponential value into an integral and solving it. You don't need math, you just need logic, right? So the law of large numbers. Now I'm gonna pick out people. um, Sebastian Ibar. Yes, you have to isolate stuff. So Sebas, can you tell me what does the law of large number states? And I want you to open up your mic.
Hi.
So Sebas, do you remember what this? Yeah, sure. You can open up your PowerPoint presentation from the class if you'd like.
Hi. Do you hear me?
Yeah, perfectly.
Okay. What I remember about that law is that I don't have my PPT open, but what I remember is that it says that if we repeat certain times the probability of a number,
Mm-hmm.
you will get a constant, I guess.
Something like that. Do you guys, for example, remember when in econometrics 1 you saw maximum likelihood?
Yes.
Okay, so maximum likelihood, what it says is that you can fit a set of values into a distribution. So you're assuming a mean and the standard deviation or any set of values depending on which distribution you're fitting it into. And you're assuming it will look like that distribution. Now, the law of large number, you have the weak law and the strong law. So basically, they both say the same thing, but one is more strict on the things that you have to comply with in order to get that strong or weak assignment. So what the strong law says is that if you repeat any experiment infinite times or approaching to infinity, taking say some data from from a sample distribution, not a population distribution, you will reach the population mean by repeating it infinitely. Say, for example, the average age of a Peruvian is I'm just planning out values. It's 40, for example, and you have a sample because you cannot go through every single citizen on the country and ask them their age, right? It's impossible. So you have to take out a sample of people. Now, the strong law says that if you're increasing that number and that number of people on your sample is large enough, then on all cases, your population mean will be the same as the I mean the your sample mean will be the same as the population mean. So the probability of the limit of the sample mean when n goes through infinity equal the population mean will always be 1. So that's the strong law. Now the weak law assumes a little bit less stuff. So the weak law, what it says, so instead of limit of probability, instead of a probability of limits, it's a limit on probabilities. I'm gonna write them down in a sec, but the weak law, what it states is that the difference in between your your sample mean and your population mean in absolute terms should not be greater than an epsilon, so a really small value. So you have a little bit of leeway with the weak law, and I do not know. Maybe I do know, but I cannot come up with an example right now of something that follows the strong law of large numbers. But it's easy to find something that, yeah, it has something to do with lim. Um, yes. Oh, what is I going with this? So yeah, there's a lot of examples of the weak law covering in reality. However, it's much less likely to find something that covers the strong law. So I'm gonna go back to this and next color, blue. So strong law is that the probability, the limit how do you write limit in latex? This is really to find, don't worry. Limit. Limit when n tends to infinity of x if, say, how do I do x hat? I do hat. Yes. Hat of x and this will be mu in all the cases. Okay, so equal to 1. Now, on the weak law, you have something a little different. So on the weak law, you get, do I have this on green? On the weak law, you have that the limit when n tends to infinity the probability of absolute value, so like this. Where's absolute? There we go. Of x of n minus mu. This one is less than epsilon on basically no cases. It says wheel over here. Okay. So what are the assumptions? So basically, you need that your data has to be IID, which means independently and identically distributed. So it cannot be that the age of somebody depends on the age of somebody else. It cannot be that the age of Juan follows a uniform distribution at the age of somebody else follows a random normal distribution. They have to come from the same distribution. They have to be IID. And also, this is really important, or else you cannot do this. Distribution needs to have a valid first and second moment. That means that the mean or the variance cannot be infinity. So extrapolate. Yes, yes, that's right, Fernando. Oh, my bad. This is greater than. Yeah. If we write less than or equals, then it's 1, right? But if we write greater than, it's 0. We good over here? Any doubts on the strong law and the weak law of large numbers? Okay. Central limit theorem. I'm gonna pick out one of you again. Estuardo, open up your mic and tell me about the central limit theorem. Estuardo? Okay, there's no Estuardo. Who wants to take this? Okay. Fernando called before. Fernando, open up your mic and tell me about this central limit theorem.
Okay, as long as I am concerned, I remember that it is about the central limit theorem is about the mean of a distribution. For example, you have that x is distributed maybe as a normal distribution or maybe not a normal distribution, but you will have that the mean, provided that n is large enough, depending on the original distribution, provided that n is large, you'll have that the mean of x will approximate. I mean, its distribution will approximate to a normal distribution.
Yeah, that is correct. So so what they teach you usually in stats is what Roy says, that n has to be greater than 30, or some say 32, and then your data approaches a normal distribution. Yes, so 30 or 32. This is not what the central limit theorem says. It's more what Fernando says. So if you have so the actual original theorem talks about a standard normal distribution instead of a normal distribution. So if you have any values, so your what is it? The sample mean. So if you have the sample mean of any distribution and n tends to infinity, so your sample is large enough, and you standardize it, so you take away the mean divided by the sample variance, so the probability of that being smaller than x should follow a standard normal distribution. So basically, when n is large enough, a, a standardized version of your data should follow a standard distribution. I'm going to write this down. So this is, again, I'm going to copy my limit of n tends to infinity. The probability of our sample mean minus mu, all of this divided by our sample variance. Remember, it's sample variance. So sigma divided by n. The probability of this being less than or equal to x. So this is basically the, like you're making an density formula, okay? It should be equal. And I'm using phi as the standard normal distribution, okay? The sum of variables is referred to instead of just one variable. What do you mean about sum of variables?
I mean, I think in econometrics one, Castro referred to the central limit theorem by saying that it had to be a sum of variables, like
So
I don't
say
know,
you
x
have
plus y.
a normal distribution on x and a normal distribution on y, then you get a normal distribution on the sum of it. That's what you mean?
No, actually, I think he was referring to the fact that by the central limit theorem, if they both had any variables as n tends to infinite, when they are summed, they have a standardized normal distribution.
Well, it doesn't have to be different variables. Yeah, it doesn't have to be different variables. So if they follow the same innate distribution, so if you have two different variables that follow the same innate distribution, if you get any of them large enough independent of the other one, then with the first variable, you could be replicating the behavior on the second one, and thus having an approach to a standard normal, given that you standardize your regular data. And in about the operation on distributions, we have some exercises that probably because of the time we're going to push some of them to the start of the next class. But yeah, there are operations with normal and standard normal variables that you can simplify with using some properties. But yeah, you do not need different variables in order for the from the central limit theorem to apply. Right. What assumptions do you need for this theorem? Any of you guys? IID, yes. You need IID. The sample size, well, the sample size is in the definition, right? You need as your sample size approaches infinity, then you have probably a valid theorem, right? Okay. All right. Any other question, guys? If there are no more questions, then we'll do one more, probably number 4, and then we'll push the rest for the next class. We'll do it at the start of the next class. Okay, so this next exercise is for operations with distributions. So you have x and y that are two independent, so YID, and independent between them as well, uniform random variables that go on the unit interval of 0 through 1. So this is the lower bound and this is the upper bound for both of them. However, it doesn't mean that when one is 0, the other one is 0. When one is 0, the other one could be 1, for example. What is the probability density function of x plus y? Okay, so let's start this out. Okay, so we have something that we need to calculate. Let's call it w. That's x plus y. Now, we know that x and y follow a uniform distribution. What's the name of this thing? Sim. That follows a uniform distribution that goes from 0 to 1, and that they are IID. What else we know is that we want to find out the probability of x plus y less than or equal to w. So this is basically the probability density function, right? Now we have to split it by parts, right? Because there are some times that we will fall in this interval, and then there are other times that we will fall in the interval of 1 through 2, right? Because say one is 0.5 and the other one is 0.7, you get 1.2, right? So we have different sizes. And the thing is, we have two variables over here. So whenever we're doing our integrals to size up this probability, we have to use not one integral, but two. So we're going to divide this by parts. So when w, so the sum of it, is in between 0 and 1, and then we have this integral Now the first integral will be the range on x. So this will go from 0 to w. Because w will be moving around, and remember our upper bound right now for w is 1. And the next integral, which will be the integral of y, will go from 0, because it's our lower bound, all the way to w minus x. And the great thing about this is that we don't need anything inside. dw x. Let's put another space over here. Out of here. Okay. So that's one part, and we haven't solved it yet. Let's start solving it. Okay. This is really straightforward, right? The first integral will just be the one that's implicit over here. So the one evaluated on the interval, right? So it's since it's 1, we have that it turns, when integrating, it turns into y, and since it's at the determined integral, we have to evaluate it by the upper and the lower bound. So it's w minus x minus 0. So we turn out with, still have to write the x part. So this is the x part. For the y part, we already said that it was w minus x. And we solve this out, right? Solving the integral, we have that instead of w, it'll be wx, because w is considered a constant right now. And instead of x, it'll be x squared divided by 2. We're not done. We have to evaluate this result from the bounds, right? So from 0 to w. So if we evaluate this from 0 to w, we get w squared over 2. Now, this is just one part, right? Because the distribution changes whenever we have something that's greater than our usual uniform. Now we need the other side. So for w, that we could do greater than 1. However, we know that since the maximum of each one is 1, the maximum value of the sum has to be 2. So from 1, w all the way to 2, we have that the probability x plus y less than or equal to W should be a really simple thing. We just turn this out into, imagine that 1 minus probability of the reciprocate. So instead of x plus y less than or equal to W, whatever is left, so greater than W. Okay? Now, since we did this, we can apply the same logic that we did over here. However, we're not looking from the lower bound anymore. We're looking from the upper bound to the middle. Okay? So instead of, I'm just going to copy this out. Missing. So instead of being from 0 to W, in this case, we have that it's from W minus 1, because we never want to be, we want to be inside the uniform distribution. So it's from W minus 1 all the way to 1. We're counting from right to left instead of from left to right, that it was the other one. And the inner part should be just like the last part, from W minus X all the way to 1. And this is the same, dy dx. I have $2 signs. Now we just have to solve this out again. And I'm going to spare you the details. We don't have a lot of time. It's 2w, w to the power of 2 divided by 2. So we know that for one part is w squared divided by 2, and the other one is 2w minus w squared divided by 2. So if we put this together, then we know, also remember, this is for 0 to 1, for 1 to 2. We need to do the other ones, right? For w less than 0, less than or equals to 0, what is the probability? 0, correct. Then for w greater than 2, yeah, the probability is 1. Why inside the integral there is a 1 empty? Where there's a 1 empty? Oh, yeah. So this is from stats 2. So yeah, it has been a while since you saw it. What we're doing is basically an evaluation of the areas beneath the curves of each distribution. Okay, so let's see if I can actually draw this. You have X and you have Y. And you know that all of them are capped on this section. Right? They can only be over here. Okay. When you're doing the distributions though, X and Y follow the same distribution. It's a uniform from 0 to 1. However, since they are independent, X plus Y is not a uniform distribution from 0 to 2. This is not correct. Okay? What you have to do is analyze how they might look in the plane of probabilities. So for example, in this case, you have that this is W. So W might fall in between this interval. However, W has the possibility of going all the way to 2. So you have this segment, and you have this other one. Now, not really, but it's much more like a uniform distribution from 0 to 1 than it's for the other part. However, it's not really a uniform distribution. I could plot this out, but it's probably something like this. It's probably something like something like that. But yeah, don't get confused with this. But the important part is that you have two tranches that have a different probability of happening, and thus you have to evaluate them in different parts. Because in order to reach the part of 1 to 2, then you need both of, no, not really both. You need, for example, X to be over here. Oh, my pencil. You need X to be over here, for example, and Y to at least be here, or say both of them being around here. So it depends on the pairwise comparison in between X and Y. It's much more probable that it falls in between here, right? So going back to the code, there we go. We have to evaluate it by different parts on the two tranches. Okay. All right. I'm probably going to clean this up on the weekend and upload it completely without all the next three questions because we haven't done them yet. But I think this topic will be clearer when we do the next questions. Because the logic is much simpler to see when you're looking at random normal or random standard normal variables than it is with the uniform distribution, actually. Okay, so any other question, guys? This is a joint distribution, yes. So for Sebastian's question, why it's W minus X? Because you need to cap out the possible space that it can cover. And since X is already capped out on the outward integral, then you just bound your Y towards the bound of X. How do you construct the first integral? We just went over it. Yeah, maybe I can upload you guys. Yeah, I will upload you guys some reading material on how you, and it probably has better visuals than I can make with my mouse. But I will upload you guys a material on how do you construct integrals from two different or more variables and when calculating areas. Yes. But yeah, that is basically it. It's refresh my mind. Yeah, I know. Stats 2 has been probably like 2 or 3 years ago for you guys. So I understand that it's not fresh. Yeah, I will upload some material in order to recheck that if I still have knowledge. I already registered you, Andres, as the class rep today in the morning. So you probably will be receiving some communications from the student representation. And yeah, if you guys want any questions, you probably I probably already gave you guys my number, so you can just ask me anything. Please, Mr. Rea. And yeah, I'll be probably really available from Friday to Sunday since it's holidays. Yeah. I will upload the latex file. I will upload the PDF since I don't expect you guys to have all the infrastructure set up for latex. The thing is, if you want, I can upload the latex file as well, and you can read it in any text editor. However, in order to generate it and to from a .tex file generate a PDF file, you do need a compiler and you need to install any latex interpreter. The smallest one is called mictex or something like that. Yeah, it's called mictex. That's the smallest latex compiler. And the one I recommend for you guys in order to try stuff out, so you guys don't have to install anything, is called Overleaf. Now that works online, so you don't have to install anything in your computer. Sometimes installing latex is quite challenging. I don't know if you guys have ever tried to install Python, and it's usually not really friendly. latex is Installing latex is much less friendlier than installing Python. So I suggest you guys to use Overleaf. But yeah. Um yeah. See you guys later. What book do I recommend? There are multiple books that I'm going to be recommending for each part of the course. For this part on a specific, so probabilities and stuff, I recommend this one. Hold on. Books. I think it's this one. Yes. The root, probability, and statistics. We will be uploading the book titles in the syllables whenever it's ready. Statistics. Statistics. Yeah. Okay. My Groot. All right, guys. I have to go. I have a conference call from work in 5 minutes. So see you guys. Have a nice weekend. Have some nice holidays. See ya.